Here is another matrix for us to play around with. We're calling this matrix A. I'm going to start by finding the determinant of this matrix because it will be useful to have that later on, and it's something that we can do quickly and easily now, hopefully. So let's go ahead and do that, and then we'll just have make a note of it and have it to use when we need it. All right, so I'm going to use this row to do my cofactor expansion because there are two zeros. The reason for that is that I'm going to take 2 and multiply it by the by the determinant of this submatrix, then add that to 0 times the determinant of this submatrix and 0 times the determinant of this submatrix. And obviously those last two terms, 0 times a determinant, 0 times a determinant, well, a determinant is a number, so 0 times that number is going to be 0. So I really only need to do this one term. So the determinant of A is 2 times -1 to the power, what position is this number in? It's in row 3, column 1. So that means I'm going to put a 3 plus 1 up here. And then I'm going to multiply that by the determinant of that submatrix. That's going to be 0, 1, -1, 3. I'll do that arithmetic. That's 2 times -1 to the power of 4. That makes this a positive 1, and I don't need to write it in the next step. My determinant is 0 minus -1. So I get 2 times 0 minus -1, which is 0 plus 1, which is 1. So I'll make a note up here that the determinant of A is equal to 2. And we'll have that now ready when we need it. What I'm going to do next is find a matrix. I'm going to call it C. In fact, I'm going to call it C sub A. That's also a 3 by 3 matrix. And this matrix is going to be made up of the cofactors of each entry in this matrix. The cofactor, remember, is the part of, I'm not sure how to describe it without just giving you the formula. You have the cofactor of an entry, right? So the cofactor of the let me rewrite that, the ijth entry in matrix A is equal to -1 times I plus j times this thing we called the minor sub ij. And the minor was that subdeterminant. So let's find the cofactor for 2, because that way I can help to distinguish the finding of the cofactor for an entry in a matrix to finding the determinant of a matrix. The cofactor of 2 is it's the cofactor of the entry in position row 3, column 3. Sorry, column 1. Row 3 down here, column 1. That's going to be 3, 1. That's equal to -1 to the power of 3 plus 1 times the minor. And the minor is still, as it was a minute ago, the determinant of this submatrix. And that is 0, 1, -1, 3. This is an even number, so this is a -1 to an even number is just 1. So I can either write 1 times or I can omit it. I'm going to omit it this time. And the determinant of this little matrix is 0 minus -1. So the cofactor, this number right here, for this entry is going to go in my cofactor matrix right here. And the distinction that I'd like to make is that I have found a cofactor. Not a determinant. I only used the 2 in finding the determinant as well, but that was because these two entries were 0. If one of these had been a non-zero entry, or if I had chosen a different row or a different column, then I would not have been able to do that. I had to use 2 to multiply by this cofactor in order to find the determinant. And I also had to add the two terms with these coefficients. It's just that they turned out to be 0. So the determinant is 2, but the cofactor for that same entry is 1. I hope you can see the difference there. Let's do one more together. Let's look for, I'll use yellow here. Let's look for the cofactor for this position. So I'm in row 2, column 3. My cofactor for row 2, column 3 is going to be -1 to the power of 2 plus 3 times the determinant of what's left over. Let's see, I'll do it this way. Those are the entries left over when I cross out row 2, column 3. So my determinant is 2, 0, sorry, I was using yellow there. Let me switch back to white. 2, 0, 2, 0. All right, so I'm going to have this time negative 1 to the 5th power. That's an odd number, so that's going to be a negative. But my determinant here is 0 minus 0, so that's 0. And 0 is neither positive nor negative, so the thing that's going to go in this position here in my cofactor matrix is 0. I'm going to do this for every entry in this matrix. Every entry in this matrix is going to have an entry in the same position in its cofactor matrix that gets built that same way. I'm just going to do that off screen and I'll be back in a minute. I would encourage you to verify these values just as practice. It's not absolutely mandatory, of course, but if you want to make sure that you know how to find a cofactor matrix, not something we've done before, that you know how to find cofactors specifically and not a determinant, then finding cofactors is part of finding a determinant, but they're not the same thing. So it wouldn't be a bad idea to confirm these values. What I'm going to do now is I'm going to take that cofactor matrix of A and I'm going to transpose it. In other words, I'm going to find a new matrix that's made up of columns that match the rows in this matrix. So instead of a row 0, 6, 2, I'm going to have a column 0, 6, 2. The next row is 0, negative 2. That becomes my next column. 0, negative 2, 0. And then 1, negative 6, negative 2 becomes my next column. And the reason I've done all of this, it's certainly not transparent, is that it turns out that if you take a matrix A, there we go, if you take a matrix A and multiply it by this matrix that you've created in 2 steps, you've created by finding first the cofactor matrix of the matrix and then the transpose of the cofactor matrix. By the way, this is called the adjoint matrix of A. That's ADJOINT, adjoint. It turns out if you take matrix A and multiply it by its adjoint matrix, or in fact, if you take the adjoint matrix of a matrix and multiply it by the original matrix, in both cases, you're going to get this. I'm going to show you with this particular example. It turns out in this case, this is very handy, that the multiplication of these 2 matrices, this is a matrix and this is a matrix, so this is matrix multiplication, that it is commutative. We're going to get the same result whether we do the matrix multiplication from the right or from the left. All right, so let me do this matrix multiplication with A and its adjoint. So we have A times this other matrix called adjoint A. This is my matrix A, this is my adjoint A. Now I'm going to do this multiplication, but I'm not going to do the whole thing on screen. I'll do part of it. I don't hope we don't need to spend that much time together practicing matrix multiplication. But by way of reminder how you find each entry, I'm going to take each entry in the first matrix here, in row 1, and entry by entry, multiply it by the entries in the column of the first column of the second matrix. So 2 times 0, 0 times 6, 1 times 2. 2 times 0 is 0, 0 times 6 is 0, and 1 times 2 is 2. When you add those 3 values together, you get 2. And that value came from multiplying the entries in row 1 of the first matrix, column 1 of the second matrix. So it's going to go in row 1, column 1 of my resulting matrix. Let me just do one more kind of randomly chosen entry for this matrix, and I'll do the rest off screen. So let's do, let's see, which one shall we do together? Let's do row 2 in matrix 1 by column 3 in matrix 2. So row 1 by column 3 means 0 times 1 plus negative 1 times negative 6, that's 6, plus 3 times negative 2, that's negative 6. 0 plus 6 plus negative 6 is 0. And that came from row 2 here by column 3 here, so it goes in my row 2, column 3 position. All right? Let me finish doing this off screen so that we're not spending all our time just doing arithmetic. And I'm going to do this last entry with you just to convince you it's really real. This is row 2, column 2 in my resulting matrix. I have to go with row 2 times column 2, row 2 in my first matrix times column 2 in my second matrix. I'm going to get 0 times 0 plus -1 times -2, that's 2, plus 3 times 0. So I get 2 here. And the result is a matrix with 2's on the diagonal and 0's everywhere else. Well, remember that the determinant of A was 2. So this is the determinant of A in every entry, or I could write this as 2 times, I need to make a little bit of room for myself. My tools for this app end up all over the screen and you can't necessarily see that, but I could write it this way, where 2 is just scaling this matrix where it's only got 1's on the diagonal. Well, that's just the identity matrix. So that's 2i. I'm not going to do the work here, but I would encourage you to try this at home. It turns out that if you multiply the adjoint of A by A from the left, here I multiplied adjoint A by A from the right? Remember that multiplication of two matrices is not necessarily commutative. Here it turns out that it is. So I would encourage you to try this. You should get 0, 0, 1, 6, -2, -6, 2, 0, -2. That's very messy. Times 2, 0, 1, 0, -1, 3, 2, 0, 0. Do that multiplication and make sure that you get the same thing. All right, you'll get this matrix here, which can be thought of as this matrix here scaled by 2, which is just 2 times the identity matrix. Now, it's worth pointing out that in this case, we knew the determinant of A was 2, and so when we ended up with this, we were able to write this as 2 times I. But in general, it happens that the adjoint of a matrix times the matrix is equal to the matrix times the adjoint of the matrix. Oops, left off the A there. But that equals the determinant of the original matrix times I. Now, I think that's pretty cool in and of itself, but you might be wondering, why the heck would I care? Well, let me show you. I'm going to take parts of this equation and rewrite them. In order to do that, I'm going to need to erase the screen here. I could go to a different slide, but it would have the same effect to you. You won't be able to see the resulting, you wouldn't be able to see this information anymore anyway. So I'm going to erase this part of the screen. I'll leave A here. I'll leave a adjoint on the screen. I'll probably move it around, tidy things up a little bit. But I'm going to go do that now, clean the screen up a little bit, and then I'll show you how this information is useful. All right, so when I move things around off screen, they don't always stick. So let's see, I'll try moving things around here a little bit. There, that goes there, that goes there. Boy, that's a pain. And then I'll have to rewrite this, I guess. It's not quite where I want it to be. But what we have here now is a series of equations. We said that adjoint A times A, I'm using parentheses because it would otherwise be easy to confuse A with the capital A in adjoint, and whether it's adjoint A or adjoint A times itself, is not clear. So I'm using parentheses to make sure that it is clear. Either way you multiply that, we get the determinant of A times the identity matrix. So we have that equation, and that is a series of equations, like a string of equations. This equals this in turn equals this. So I can take any two pieces of this and set them equal to each other. I could say this equation here, or this expression here equals this expression here. What I'm going to do is take this one and this one. That's just the way that the algebra works for me. A times adjoint A equals the determinant of A times I. And the next thing I'm going to do is divide both sides by this value. This is just a numerical value, right? We found it for matrix A, we found it was just 2. So it's just a number. I'm going to divide both sides by the determinant of A. In our particular example, it would be like saying divide both sides by 2. Having done that, these two values cancel, and I'm left with, I'm going to write this as a times 1 over the determinant of a times the adjoint of a equals I, because these values cancel, right? So I just have I left on that side. Now, something else that we could do here, remember that this is just a constant value. So if I took, let's say for the moment that's 2. It is in our particular case anyway. And that would make this 1/2. 1/2 times a matrix is just a scaled matrix. So what I have here is a scaled matrix. A matrix times a matrix is a new matrix. But remember also by the properties of matrices that if one of the things you're multiplying through here is a constant, you can change the order you're multiplying it in. So I'm going to write this now as 1 over the determinant of a times the adjoint of a. That still equals I. That's just a property of matrices. That lets me put this constant over here. We made the observation earlier. I didn't prove it, but I made the observation earlier that adjoint A times A and A times adjoint A, no matter which order you multiply them in, they're equal. So I'm going to rearrange this expression so that it says adjoint A times A, that's still equal to I. And then I'm going to multiply this equation, both sides of this equation, by the matrix A inverse from the right. And the reason for doing that is that the right-hand side now is just A inverse. And since A inverse is I, when I multiply a matrix, here's a scalar times a matrix, when I multiply this matrix by the identity matrix, I just get that matrix back. So what I have here now is this equation that tells me that one way to find the inverse of a matrix is by finding its determinant and sticking it in the denominator, then finding its adjoint. Scaling the adjoint, you have the inverse. Let's take a look at an example of how this might actually be useful. Here's a 4 by 4 matrix. It's not too ugly. It's got a lot of zeros in it, a lot of ones in it. That's pretty nice. But if you're asked to find n inverse, the only technique we had before today was to take 1, 2, 2, negative 3, 0, 2, 1, negative 1, 0, 0, 1, 0, 0, 1, 0, 0, and augment that or concatenate it with the 4 by 4 identity matrix. Writing really fast here. And then do a whole bunch of row operations to get this side, into the form of the identity matrix, and the resulting matrix over here would be your inverse matrix. But with the formula that I gave you today, we may have an easier way to do this. So let's take a look at that. I'll start with the reminder that A inverse, and A is just a generic matrix, A inverse is equal to 1 over the determinant of A times the adjoint of A. And sometimes, as in this case I think, it will be easier to find the determinant and the adjoint of this matrix than it would be to push through a whole bunch of row operations. So let's start with the determinant. Now we're not dealing with matrix A here, but matrix N. This is just a generic formula, right? This is just here to remind us of all the pieces that we're looking for. The determinant of N, we can find that a couple of different ways. I'm going to do it using the sort of the first technique we learned, but I'm going to adjust that slightly to notice that instead of choosing to work with a row that has a 1 and everything else is a 0, I'm going to use this column. And the reason I'm going to use this column is because that 1 is in the first or last position. If I use, let's say, this row here, then I'm going to have to multiply 1 by the determinant of the matrix formed by these entries. Whereas if I choose this one in the corner here, I can just use this matrix, right? It's a little easier to see. That's the only reason for choosing that. So I'm going to get 1 times the remaining matrix, the remaining determinant here, which is 2, 1, negative 1, 0, 1, 0, 1, 0, 0. Now I have to find this determinant, right? This is a subdeterminant of a 4 by 4 matrix. Again, though, I have a 1 in the corner. So this is going to be equal to this 1 right here times this 1 right here times, I need a pen or a highlighter or something, this subdeterminant, or the determinant of that submatrix. So 1, negative 1, 1, 0. That's 1 from here times 1 from here times 0 minus negative 1. So that's 1 also. So my determinant is 1. Well, that's nice. The determinant of n equals 1. And it's particularly nice because I need to plug that into this formula, and I'm just going to have 1 over 1, which is 1. Remember that another way to find the determinant of a matrix is to rearrange it so that it's in triangular form. Here I'm almost in triangular form. This 1 is in the way. So if let's see, how could I do this? I could reverse these 2 rows, and I could multiply this row by negative 2, which would get rid of, and add it to this one, which would get rid of that there. Sorry, it would get rid of this, but this row is now down here. I made a row change, so that would change the sign. Then I would multiply here. There are actually a couple of different steps you would have to do. But doing some row operations on this would put it into triangular form, and then you could just multiply these values here together. You would get a negative 1, but because we made a row change, that requires a sign change. So that tells us our determinant is 1. I'd welcome you to try that just as practice. But it turns out with this particular matrix, this method was a lot easier anyway. Now we need to find the adjoint of A. And just as a reminder, oops, wrong pen. The adjoint of A is equal to what you get when you take the cofactor matrix of A and transpose it. So the first thing we have to do is find the cofactor matrix, and then we'll transpose it, and that will give us our adjoint. So let's find the cofactor matrix. If A has 16 entries, its cofactor matrix will have 16 entries, 1 cofactor for each entry. I'm just going to take maybe 2 or 3 of these. I'll start with the top left-hand corner. Just a couple of them to remind you how it's done. This is a bigger matrix than we've worked on before as well. So let's find the cofactor for this position here. I'm going to highlight that, and then I'm going to, how do I want to do this? I think I'll also highlight the remaining matrix, if you will. The submatrix that's left when you cross out both the row and the column that first entry is in. I'm going to look for the cofactor of this entry, which is negative 1 to a power times the minor, right, the determinant of this matrix. So I'm going to have, for cofactor 1, 1, I'm going to have negative 1 to the power of 1 plus 1 times the determinant 2, 1, negative 1, 0, 1, 0, 1, 0, 0. And that determinant is pretty easy to find. This is negative 1 to an even power, so that's going to be 1. And this determinant here is, because of all these zeros, you could use this row or this row, I'm going to use this row, is 1 times this subdeterminant, which is 1 times 0, which is 0, minus negative 1 times 1. 0 minus negative 1. 0 minus negative 1 is 1. So I just get 1. So it's coincidental that this number here is the same as this number here, but that goes right there. All right, let's do another one. In order to do this, I'm going to need more room. So I'm going to erase the scratch work I did here. And all right, that gives me some more space. Let's pick another one to work on together. Let's do a 0 because it's tempting to say, oh, my entry that I'm working with is just therefore my cofactor is going to be a 0. Well, that's not necessarily the case. It might be, but it might not be. So let's work on this one together. We're looking now for the cofactor for entry row 3, column 4, 3, 4. That's going to be equal to negative 1 to the power of 3 plus 4 times the determinant that's left over when I cross out. Let me do this in sort of pen, if you will. Cross out row 3, column 4. And what's left is this submatrix. I want the determinant of that submatrix. So that is going to be, I have one wrong pen, 1, 2, 2, 0, 2, 1, 0, 1, 0, and that nicely has a row in it with only one, or a column with only one, 1. In fact, I think I'll use that column. I've got it in a corner again, so it's easy to see the determinant. So I'm going to use the fact that negative 1 to an odd power is negative. Just to put a negative there, I could write a negative 1, but I don't really need to, times 1 times the determinant of this matrix. And the determinant of that matrix is 0 minus 1. So here I get 1. That goes in the position in my cofactor matrix in the position of row 3, column 4. Row 3, column 4 is 1. And notice that it's a 1, not a 0, in spite of the fact that the original matrix has a 0 in that position. All right, I'm tempted to do another one just for practice. Let's just do one more. Let's do the cofactor for this entry here. All right, so I've set this up for us. I have row 1, column 4, so I have cofactor 1, 4, which starts with negative 1 to the power of 3 plus 4, and the matrix comes from what's left over. When I cross these out, that is this matrix here, submatrix. Oh, that's messy. It's okay. And that is the matrix 0, 2, 1, 0, 0, 1. I know it looks like that 0, 0, 1 row is crossed out, but that's the yellow cross out. That's the one I did the last time. And 0, 1, 0. Now, I don't need to do anything else. I can make the observation that this is an odd number. That means this is going to be positive. But by properties of matrices, I have a column of all zeros. Therefore, I know that my cofactor here is going to, the determinant of this matrix is going to be 0. So in row 1, column 4 of my cofactor matrix, I have a 0, even though the entry itself was not 0. So you can't just assume something from one of the entries that you're going to end up with something sort of related to that entry. All right, I'm going to do the rest of these off screen. And when I come back, we'll have a completed cofactor matrix and we'll go from there. So here's our cofactor matrix, and I'm going to erase this scratch work that I have down here in finding one of those entries. And what I need to do now is find the transpose of this. Remember that the transpose of the cofactor matrix is called the adjoint. And that's going to be the same matrix, but instead of columns 1, 0, 0, 0, sorry, rows 1, 0, 0, 0, I have a column 1, 0, 0, 0. Instead of a row of negative 3, 0, 0, 1, I have a column. And then I have 1, 0, negative 1, and 1. And typically, not giving myself enough room, negative 4, 1, 0, 2. That's my adjoint. So to find the inverse, I need to take 1 over the determinant. The determinant is just 1. And multiply it by the adjoint. So in this case, n inverse is just 1 times the adjoint. 1, negative 3, 1, negative 4. It's the same inverse. It's the same matrix. Right? It's the same as the adjoint. 0, 0, negative 1, 0, and 0, 1, 1, 2. Can you even see that matrix notation there? So finding the inverse of this matrix, we had two options. We now have this, this possibility where you can find the inverse of a matrix by taking 1 over its determinant, which in this case was 1 over 1, and multiplying that by the adjoint. The hard work here is in creating the cofactor matrix for each entry in, I should do that over here. For each entry in the matrix, I have to find the cofactor for that entry, create a matrix out of that. That takes a little bit of time. It's a little bit tedious. A much bigger matrix, and it would be, more tedious still. But this one wasn't too bad. Finding the cofactor matrix, from there we take the transpose of that, and then we just multiply that scalar by the adjoint, by this transpose of the cofactor matrix. So that's the new technique. The old technique is to take this matrix and concatenate it with an identity matrix out here and then push through row operation after row operation after row operation until this side is the identity matrix and it reveals the inverse matrix on this side. So you now have two options for finding the inverse of a matrix, assuming it has an inverse. You can refer back to the invertible matrix theorem to help you determine whether or not there in fact is an inverse for a matrix. One way to find out that there isn't would be to do either of these steps and get some kind of weird answer here. But you can also refer to the invertible matrix theorem. Okay, that's going to do it for this video. And we're going to talk next about Cramer's rule. Then the next section is Cramer's rule.